Sorry about that. I just talked around and I wanted to make sure. I was scared that the recording, I wasn't sharing my screen, but I was. So that's why I ended really abruptly. So let me share my screen again. Slides. Start. Okay, good. So, this is where I left off. Least common multiple. As I was saying, I've looked through the homework, and what the issue with the least common multiple, and this is why things got real messy, was when it comes to the variables. So we can see on this next slide, right? We've got this finding the multiples, and we've got letters in the problem. Now I've looked through all the homeworks, the exams. This is not going to show up. This is not going to show up. So I'm going to go over the easy way to do this with just regular numbers. And so least common multiple, let's talk about it. A multiple of a number. This is just, you have your number that you're finding the multiples of, take the number 10 for now, right? 10. I want to find multiples of 10. It is literally just 10 times 1 times 2 times 3 times 4, and so on. Those are all multiples of 10. Now, the easiest way to go and find the multiples of 10 here are just counting by that number, right? Counting by 10s is really easy. This is 10, 20, 30, 40, and so on. And there's an infinite amount of them. Because we could pick any number to multiply it by as a multiple. But counting by that number is the easiest way to go about for what we're doing this here. A common multiple, right? So we've talked about multiple, common multiple. So when we're talking about common multiples, we're talking about two numbers that we're finding the multiples of. Let's do 20. Let's do 20, right? Common multiples. So let's find the multiples of 20. Let's count by 20. 20, 40, 60, 80, and so on, right? So common multiples are numbers that show up in both of these lists, right? So 20 is a common multiple of 10 and 20. 40 is a common multiple of 10 and 40. 30 is not, right? 30 is not in this list. So that's a common multiple. Least common multiple. Adding the last word into here, right? This is the smallest of the common multiples. So in this random example I made up here, right, the 10s and 20s, the least common multiple is 20. It's the smallest number that shows up in both lists. 40, 60 is going to show up in both lists, but that's bigger than 20, right? It's the smallest number, the least common multiple. So with the example here with 4 and 8, it's got written out, but I'll do it as well, right? So we got counting by 4 is 4, 8, 12, 16, 20, 24, and so on. Counting by 8, so we've got 8, 16, 24, 32, and so on. And so we've got some common multiples, right? 16 and 24 are common in both of them, but 8 is that least common number, the smallest number that shows up in both lists. So that's the least common multiple of 4 and 8. So let's do this practice one, right? The previous slide has all these letters in it. This is the example we went through in class. In the day class, I believe. I missed the least common multiple. I picked out the wrong one, so that was a little embarrassing. The other class figured out that I was wrong here, but the least common multiple. This is why we didn't fully answer the question because I picked a number way bigger. It wasn't the least common. I picked a common multiple, but not the least one. Okay, so let's read the question. A patient admitted to the hospital, given pain medication every 4 hours, antibiotic every 5 hours, and they're getting the bandages applied or reapplied every 12 hours. Need changing, right? They need changing every 12 hours. And so the nurse changed the bandages. They did all 3 of these things at 6. Last time they did all 3 of them was at 6 a.m. on a Monday morning. And so the one thing we can use the least common multiple is to figure out when we would, even though they're all happening at different time intervals, when they would all happen again at the same time. And so if I find the least common multiple of 4, 5, and 12 hours, right? 4 hours, 12 hours, and 5 hours, that least common multiple will be that next time that they apply all three of them at the same time, give them the two medications and change their bandages. So I'm going to count by fours. I'm going to find the least common multiple by counting by fours. I'm going to count by fives, and I'm going to count by 12s. So let's count by fours. 4, 8, 12, 16, 20. That'll be enough. Count by fives. 5, 10. Sorry, give me 1 second. 15. Oh no, we got this one right. We got this one right. We didn't. It's a different problem further on. So we're gonna need more. We're gonna need more. Let me restart here. Sorry about this. If I figure out how to edit the video, I'm gonna cut this out. If not, I'm sorry. So we're counting by fours. 4, 8. I'm gonna get rid of the commas because I'm writing with a mouse. 4, 8, 12, 16, 18. That's not a multiple, that's not counting by fours. 20, 16, 20, 24, 28, 32, 36, 40, 44, 48, 52, 56, 60, and so on. Okay, let me throw the comments in there so that we can read these. Okay, fives. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. And then counting by 12, 12, 24, 36, 48, 60. And you can note here, I stopped at 60 for all of them because that is going to be the smallest number that is in all three. I knew that ahead of time, so that's why I stopped ahead a little bit early for some of them, right? So 60 is this common multiple, least common multiple. There's no smaller number that shows up in all of them, right? We have numbers like 24 in both of them, but it's not in 5. It needs to be in all three of them. Okay, so 60 hours later. 60 hours is the least common multiple. So 60 hours later, all three will happen at the same time again. Again, this question does ask what day and time. I'm not going to worry about it. What's important here is 60 hours later. That's a few days, a couple of days. And then some change. So 60 hours is the important part of the problem, though. So writing equivalent fractions, again, these have letters in them. Writing equivalent fractions, though, I'm going to only worry about numbers. And we talked about this when we saw the slide that had the 1/2 circle, the 1/4, the 1/2, and then the 2/4 one, and the 4/8 one. All we're doing here is, so we're finding equivalent fractions, 1, 2, 3, 4. And all I need to do is make sure we're multiplying the top and bottom by the same number to make sure it's an equivalent fraction. But now what we're going to do is have these we're going to have 2 or more fractions, and we want them to all have the same base, right? So obviously, to go from 1/2 to 2/4, I multiply the top and the bottom by 2. But sometimes that's not that easy. Sometimes we have 3 fractions. And so we need to figure out what the common base is that we want them all to be. And that common base will be the least common multiple of the denominators of all the numbers. So I'm going to go ahead and go past this because I don't want to worry about the letters. It's making things more complicated than they need to be, and you will not see them. So what I'm going to do here is go straight to adding and subtracting fractions with unlike denominators, okay? So when we add and subtract fractions, okay, we've got a couple subtraction problems with fractions here, okay? Now, to add and subtract fractions, they need to have the same bottom, right? 7 and 2. These are not the same bottom. So I need to write 5 over 7 and 1 over 2 as equivalent fraction, find an equivalent fraction for both of them where the bottom is the same. And that bottom, so I need to figure out what that bottom will be. And that bottom will be the least common multiple of 7 and 2. So let's count by the 2's. 2, 4, 6, 8, 10, 12, 14, and it could go on. And 7 is 7, 14, 21. This could go on too, but I already see one. 14. 14 is that least common multiple. Okay, so what I'm going to do is figure out what 5 over 7, the equivalent fraction of 5 over 7, where 14 is the bottom. And so now I'm going to ask myself, how do I go from 7 to 14 in terms of multiplication? I'm going to go, because I'm going to multiply, I need to multiply the top and bottom by the same number for it to be an equivalent fraction. So I need to figure out how did I go from 7 to 14, and that'll tell me what to do with the top. I multiplied it by 2, right? 7 times 2 gets me 14. So I need to do that with the top as well. 5 times 2. So that'll tell me what the top will be, 10. And again, if this 7 times 2, sometimes it's not as obvious what it is. If you're not sure, you could always just either take 14 divided by 7, that'll give you the answer too. Or you can just count. This is going to be, 14 is going to be the 7th spot here, right? So 1, 2, 3, 4, 5, 6, 7. This was the 7th number here. Or I'm sorry, I did the wrong one. It's because we started with 7. Sorry. I started with 7. It's the 2nd spot, right? When I'm counting by 7s, it's the 2nd spot. Because we had 7, I counted twice to get to 14. So let's look at 1/2 then too. So I know I want it to be 14 on the bottom. I need to figure out what the top is. And to go from 2 to 14, I multiply that by 7. 14 is the 7th number in the list for counting by 2's. So I need to do that on the top as well. And that'll tell me what the top is. 1 times 7. 7 over 14. So let's rewrite this with our fractions that have the same bottom. So it's, don't forget this negative sign up front. I kind of ignored it here, but negative 10 over 14 minus 7 over 14. Now that we have the same bottom, when we're adding or subtracting, they are, you keep the same bottom, the answer is going to have the same bottom, so 14. And you just add or subtract the top, the tops of them here. So I'm just going to take, remember here, be a little careful if the fraction is negative. We talked about this slightly at the very beginning of the last video, I guess, right? When a fraction is negative, like this right here, and it's out in front, this could go in the top and bottom, top or bottom. I always write in the top. So anytime I see negative 5 over 7, I'm always just going to put that negative with the 5 anyway. So this becomes a little bit more clear. And that's why I do it. So this is going to be negative 10 minus 7, right? Negative 10 minus 7, just subtracting the top because we're subtracting. And let's break this down like we did in week 1. We have negative 10 minus 7. We have, we turn it to addition. That's how we dealt with it. We kept the first one, changed to addition, and then we used the opposite of 7, so negative 7. And then The addition rules apply, which because these are the same sign, we're going to add 10 plus 7, which is 17. And because they were both negative, it's going to be a negative 17. So negative 17 over 14. And again, we should double check that everything is reduced. This is reduced all the way. I'll tell you, it is reduced all the way. So let me, I should have enough space here. Let's do the 5 over 6 minus 3 minus negative 3 over 9. So we can see in this one, right, they threw the negative sign on top. Otherwise, it would get messy. But that's why it usually goes on top. You could put it in the bottom, but it gets messy. So I need the same bottom. So I'm going to rewrite this where they have the same bottom. And I need to figure out what that will be. And that is the least common multiple of the two bottoms, 6 and 9. So 6, 12, 18, 24, blah, 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 9, 18, 27, but I can keep going, but I see 18. 18 is, so I know 18 is this common bottom that I need. So let's look at the 5 over 6 one. How did I go from 6 to 18? 6 to 18? It's the third number in the list, or, 6 times 3. 6 times 3. So I'm going to take 5 times 3, which is 15. So that's going to be the top of this fraction. And then, so now I'm looking at the other one. 9, negative 3 over 9. How did I go from 9 to 18? Times 2. I'm going to take times 2 on top here. Again, 9 times 2 is 18. It's the second number in the list. So negative 3 times 2 is negative 6. Negative 6. So now they have the same bottom. It's going to be 18 on the bottom. And I'm going to do 15 minus negative 6. And we can break it down again like I did here, but I'll go ahead and just give it to you. This is going to be 15, 21. 21 over 18. This one can be reduced. Let's go ahead and figure it out. 21 and 18. This is 3 times 7. This is 2 times 9, which is 3 times 3. So with that prime factorization, I'm rewriting 21 over 18 to be 3 times 7. And then 2 times 3 times 3. And we can cancel out, so it can be reduced. Yep. So 7, 2 times 3 is 6. 7 over 6. And this is my final answer. So again, I went through that one a little bit quick. Go ahead and rewind that one if you need to see it again. Again, I skipped through these slides. I think they just need to be cut entirely, so I am going to just skip past them. Order of operations. We're talking about order of operations all the time. So the problems you'll see will be just you do the PEMDAS. It does, nothing's really changing with PEMDAS. Okay, so decimal notation and round. So decimals. So the most important thing here is knowing what these words, what each digit means, and the word that goes with it. So if I have a number like 1, 2, 3. 0.1, let's pick different numbers. 3, that's the same. 4, 5, 6. 4, 5, 6. 1, 2, 3.456. Right. I'm looking here at the decimal point, and then I'm going to go to the left first, right? Because this is what everyone's pretty good with, right? This first spot is the ones place, right? Here's the decimal. This is the ones place. So this 3 is in the ones place. That first one to the left of the decimal. This is the ones place. And so this is telling you that 3 has the value of 3 times 1, right? Which is just 3. The next place over, this is 2. This is the tens place, right? Tens place. And it's telling you that the digit 2 in the tens place tells you have 2 times 10, or 20, right? So let me write, I'll write 3. This is 20. And this keeps going, right? This is the hundreds place. So this is 1 times 100, which is 100. So, and we could keep going if there were more numbers, right? And so in essence, we add these all up, right? 100 plus 20 plus 3, this is going to be 123. So I've just broken down the number until what each digit value represents. And so it goes ones, tens, hundreds, thousands, 10,000s, 100,000s, millions, and so on, like we know. So now, so that's not too bad. Most people can recognize that. However, it's going to the right of the decimal. It's a little bit trickier, but it's following this same pattern with a key exception. Is that this is, and we're going to go throw PHs on the bottom of each of these words. And we can see tenths, hundreds, thousands, 10,000s. So we're counting up in that same way. However, this first spot is not the oneths or anything. That doesn't exist. It starts with the tenths. So we're going to the right of the decimal. That 4 is, it represents 4 times 1/10, right? Because it's the tenths place. So it's 4/10. And for now, I'm not going to simplify these to emphasize this. This is 4/10. 5 is the 100. So it's 5 times 1/100. 5/100. Again, I'm not simplifying. And it goes on in the same pattern. So it goes tenths, hundreds, thousands, 10,000s, and so on. So there's this special way to read decimal numbers. I tend not to do this because it's cumbersome. But I can try to for this, right? So for this number here, we've got 1,000 and see, this is why this is cumbersome, right? We tend to say 1,028 and it's supposed to it's technically supposed to go only for the decimal. So you're just supposed to steady it, right? 1,028 and 4/10. 2 and 736 10,000ths. It's a little trickier, and this is why I don't read it. But negative 478 thousandths. So that's how you take it. You're not going to I'm not going to, there's no verbal exams. So you're not going to need to know it, but you need to know what each of these places are. And so I'm saying, I guess I'll point out what I'm saying here at the end here is that rightmost digit, whatever place that is. So it was 2 and 736 10,000ths, because this is the 6 is in the 10,000ths place. This was 4 and 4/10 and 8 thousandths. I'm saying the whatever the rightmost digit place corresponds to. So writing decimals as mixed numbers or fractions. So this is why one of the main reasons why it's very important to just know the names of the what do you call it? The digit places, right? The tenths, the hundreds, the thousands, because it tells you exactly how to write the decimal, right? So with the example we had 123.456, what I did with that 10th place was I took 4 times 10, or I'm sorry, 4 times 1/10, right? It was the 10th place, so it's 1/10. And that was 4/10. And so changing a decimal into a fraction is just that simple. You like the last slide, we looked to the rightmost thing, and that's the number that tells us what number we are going to put on the bottom, right? So 3/10, 3, and just kind of ignore the decimal, right? I'm ignoring the decimal. If there's a 0 here, 0 point something, I'm going to ignore the 0 too. Ignore the decimal. 3/10, right, is the 10th place. 0.67, ignore the decimal. This is 67/100, because this is the hundredths place. 0.048, ignore the decimal, ignore the 2 zeros here. 48/1,000, right? Because this is the thousandths place. And again, we should make sure we're simplifying it, but what's important is first being able to get it over to the fraction. So names are very good. It tells you exactly what number you want to put it over. One other way, make it a little bit as like a double check maybe, is how many digits are we over in the decimals, right? We have 1 digit over, there's 1 0 there. We're 2 digits over in this one, there's 2 zeros in my power of 10. We are 3 digits over, 3 zeros. Now we could follow the same exact reasoning for a number that's not 0 at the beginning, right? The 6.8, I could ignore the 0, or I'm sorry, ignore the decimal, 68, and it goes to the 10th place. So it's 68 over 10. A lot of times, though, this is a little bit harder to simplify. So it's easier to just take the decimal, take the whole part of the decimal, and by the whole part of the decimal, I mean whatever's to the left of it. Right, 6. We have 6 and 8 tenths. So we have 6 and 8 tenths. We have that whole part, which is to the left of the decimal, and then we have the 8 tenths part, which I put over. What's left over? And so when we have it as this mixed number, this is much easier to reduce the 6 and 8 over 10 to 6 and 4 over 5. That's a quick one to do. Whereas doing the factor tree of 68 is going to take a lot longer than the factor tree for 8. So practice. So 0.6, this is the 10th place. Ignore the decimal. This is 6 over 10. Let's go ahead and reduce this. 3 and 2. 10 has 2 and 5. 2, so 2 times 3 and 2 times 5. Those two cancel out. 3 over 5. Right. So I guess I didn't explain this. This is all just stuff we've been doing. I wrote 6 over 10 because it's in the 10th place. And then I wanted to simplify it. So I wrote the factor trees, wrote the prime factorization, where they go. And then I saw that a 2 cancels out. And then see, I just have 3 and 5 on 3 on the top, 5 on the bottom. Okay, 1.26. This is 1 and 2600. So I'm going to turn this into a mixed number. 1 and 26 hundredths, right? This is the hundredths place. This is 2 decimal places over, so I've got 2 zeros. This is 100. 1 and 26 over 100. So let's simplify this. I don't care about the 1 because I just have 26. 100. Let's start 100 over here. 26, this is even, so 2 and 13. 13 is prime, so we are done with that. 10, 100. This is 10 times 10. I'm technically using the divisibility rule here. There's 2 zeros here, so I can. So as long as there's 1, it's 10. It's 10 times 10. And then we'll break down the 10 twice. 2 and 5. 2 and 5. So I've got this 1. Still, it's just the whole number there. And then we've got 26 on top, which was 2 times 13. And we've got this 2 2s and 2 5s. And we got, missed it, a 2 that cancels out. So 1 and 13 over 2 times 5 times 5, 25, 50. 1 and 13 over 50. Okay, next one. 0.007. So this is 0 and 7 thousandths, right? This is the thousandths place. So I'm going to have 1,000 on the bottom, right? 3 zeros and 1,000, 3 decimal places over, 3 digits over. And 7, I'm ignoring this decimal and getting these leading zeros. I'm ignoring 7. 7's prime. So all that matters, so I could do factor trees for them to see if I reduce. 7 is prime. I don't need to do a factor tree for 7. 1,000, this one takes a little bit longer. I'll go ahead and do it. 10 and 100. We saw 10 is 2 and 5. 100 is, oops, skip this line. 10 and 10. 2 and 5. 2 and 5. If we think about this, right, the prime factorization is 7. If anything cancels with this 7, with the 1,000, there needs to be a 7 in the factor tree. We can see there's no 7. So it is reduced all the way. It can't be simplified any further. Ordering decimals. So ordering decimals is nice and easy. We are just going left to right. we are going left to right and lining them up. We're going to line up the decimals and we're going to go left to right. Okay, so we're going to line up the decimals. Let me write them top to bottom. I'm going to line up the decimals. 1.055. I'm kind of spacing it out a little bit. 1.5, lining up the digits as I do this. 1.557. 1.556. 1.55. And I'm going to grab my highlighter. Ooh. Where was I? This one. Okay. Highlighter. So the highlighter. So I'm going left to right. I'm starting with the leftmost digit here and seeing which number is bigger or smaller, depending on what I need to know, right? So let's go left to right. We've got a 1, we've got a 1, we've got a 1, and we've got a 1. They are all the same. I cannot tell which number is bigger yet. Okay, so when they're all the same, I have to go to the right one. I'm going to go 1 to the right. It didn't tell me anything. So now I'm looking at the 10th place here for all of them. These, the 0, 5, and 5. 5 and 5. 5, 5, and 5. Okay, so we get 0, 5, 5, and 5. We do have a different number. They're not all the same. So we've got something that's different. 0 is less than all the other numbers, right? Which are all just 5. 0 is the smallest one here. So this is the smallest here. Right, this is the smallest. Right, 0 is less than all those 5. This is the smallest number here. We're going from greatest to least. So I'm gonna put my old commas here. This will be 1, 2, 3, 4, where 4 is the least one. So 1.055. This is the least. But I can't tell between the rest of the numbers, right? They're all 5s still for the rest. So let's go one more to the right. 5, 5, 5. Okay, still can't tell. Let's go one more to the right. 7, 6. Uh-oh, there is no number here. Okay. When there's no number, this is technically a 0. This is technically a 0. We don't like to write zeros at the end of the number, just but it helps to sometimes write it there. So when you're not going to want any zeros at the end of the number like this, but it helps to visualize things to see that this is a 0 when there's nothing there. And since I'm not, this will be my answer up here. That's fine. I'm going to write that 0. So which is the biggest number then? 7, right? This is the biggest number. I don't know what changing. 7. So 1.557 is the biggest number. 1.557. What's the next biggest? 6, right? 6. So 1.556 is the next biggest number. And then we're left with that 0, right? That's the smallest out of these 3. We already figured out what the smallest out of the 4 was. That's the smallest out of these 3. So it's 1.55 as the third number in my list. So this is my answer, right? This is ordering them greatest to least, right? This is the biggest one. This is the smallest one. Second smallest. Smallest. I don't know if I said that. Biggest, second biggest, third biggest, smallest. Rounding decimals. Okay, so with rounding decimals, I'm going to look at this 153 and 683 thousandths first here. Okay, this one. This is also the other main area where you need to know the name. So the little shortcut where you're counting the digits over, and that tells you how many zeros in the 100. It gets a little bit more complicated when you're talking about this because it's going to just tell you. It's going to tell you round to the 10th place. So I need to know where the 10th place is. So the 10th place was the first decimal digit on the right of the decimal, right? So this 6 here in this case is the 10th place. So when I'm rounding to the 10th place, when it's telling me where to round, what I'm going to do here is I'm going to draw a little line. I'm going to draw a little line right to the right of the 10th place where it's telling me to round. Okay, and I'm going to look at the number to the right of my line, to the next number over, right? This 8 in this case. And I'm going to apply the following rule to 8. If I am 5 and up, I'm going to round up. If I am 4 and under, I'm going to round down. So 8 is 5 and up. 8 is bigger than 5. I'm going to round up. We are rounding up. And so when we round up, I'm just going to increase that tenths place where we are rounding by 1. So let's write what we got so far, 153.7, right? I increased that one by 1. And then I'm going to drop everything else. I don't want anything else over here. So this is my answer, 153.7. This is 153.683 rounded to the 10th, 153.7. Let's look at the 425.3843. We are rounding to the hundredths place. The hundredth is the second decimal digit, so I'm going to draw my line to the right of the 8, which is in that second decimal digit. And we'll look at the next number over 4. 4 is 4 and under. So we are rounding down. So rounding down is a bit of a misnomer. It makes you sound like instead of adding 1, we should subtract 1 from this number. No, that is not what we do. We leave it alone. So when we round down, we leave it alone, right? So I'm not doing anything with this stuff. So it's just 425.38. But I still dropped everything to the right of my line. So this is around 425.3843 rounded to the hundredth is 425.38. That's my answer. You can see the animation is just doing exactly what I said there. Okay, practice. Round 5.235 to the 10th. So the 10th, the 2 is in the 10th place here, right? That's the 1 decimal digit over 10th. 3 is what I'm looking at. Tell me if I'm rounding up or down. 3 is 4 and under, so I'm rounding down. And when I round down, I don't do anything. 5.2, and I drop everything still low. So 5.2. 0.2351 to the 100th. That 3 is in the 100th place, so let me draw my line there. I'm looking at 5. 5 is 5 and up, so I'm rounding up. When I round up, I add 1 here to my 100th place where I'm rounding. 0.24. And I drop everything else. 1.99991. I don't know if I said that enough times. To the thousandth. So it goes tenth, hundredth, thousandth. So 3 decimal places over. It's this 9. And I'm looking at this 9. 9 is 5 and up. So we are rounding up. So now this one's a little tricky, right? Because when I add 1 here, I can't write a 10 in the thousandths place because that's 2 digits, right? I has to be a 1-digit number. So what's happening here is I'm carrying over, right? This is 0. This becomes a 10, and so it becomes a 0, and then this 1 carries over. And same thing with this 9. Again, it's a 0, and then 1 carries over. Again, 0, and then 1 carries over. And finally, I'm out of 9, so I've got 2. So I know I said like this as I was kind of going along, but we have some rules which I've alluded to, but I'll say them right now, is we do not want any trailing zeros. All right, so this is what I want to make sure is my final answer, my answer line in my little box that I type in, just the number 2. Okay, so we've got that's the left side. So I'll talk about it here. So trailing zeros. We've got trailing zeros. Trailing, I'm just going to write zeros. And leading zeros. So trailing zeros are zeros on the right side of the decimal to the right of all the numbers. So 1, 2, 3.456. 0, 0, 0. These are all trailing zeros. These are all at the end of the number to the right of the decimal. I'm saying specifically to the right of the decimal because These look like trailing zeros, but this is just 123,000. If I get rid of these, that changes the number entirely to just 123. So that's why I'm saying to the right of the decimal. If they're to the right of the decimal and we have these zeros, no numbers after the zeros at all. These are trailing zeros, and I do not want them in my answer ever. And this is what happened with this 2, right? We've got 2, and then we add all these zeros to the right of the decimal. It will be marked wrong if you put these zeros here. If you have trailing zeros, just drop them and get rid of them. Leading zeros. So now for leading zeros, we're on the left side of the decimal. We have something like 0, 0, 1, 2, 3.456, right? These zeros aren't adding anything to it. It's the same idea, is just we don't want these leading zeros. Except, and there's one exception to this, and that is when we have something that is less than 1, but a positive number still. So for between 0 and 1. So when we have a number like 0.56, right? This is the one scenario where I want that leading zero, 0.56. We are always going to write 0.56. If it's 0 point something, you'll see it in your calculator. If it's 0 point something in your calculator, you'll write 0 point whatever that number is, 0.56. We need this one in here, and this is an error prevention thing, right? If you're I don't know, maybe writing down some notes and you don't put down, you're going to give them 0.5 tablets, and someone is reading your handwriting, or I don't know. I'm not a nurse myself, you remember, so I don't know exactly how it will go down. I'm just making up some things here. You write down somewhere you need to give someone 0.5 tablets of a medication, but you write it like this, and someone else comes look at it, and they don't notice that point there. They just see this 5, and they give them 5 tablets. That could kill someone. Okay, so this is why we always write 0.5 something. It's much more clear that we're talking less than 1 here, 0 point something. Okay, so again, I know I skipped around here, but I wanted to focus in on the important stuff that you'll actually be tested on. I skipped over stuff that was left over from previous terms, it seems. I'm going to stop the recording here. Please, if you go back and go through any of the problems again, that kind of a thing. I've gone through today with these 2 recordings. There's going to be 2 recordings because I separated them. Go back and rewatch any of them as you need.